Hello, this is Jeffrey Fox again, the instructor for Big Data Open Source Software and Projects. We now come to the second part of the lectures on Big Data Application Structure, which is derived from a study of the use cases from the NIST survey from the fall of 2013. So the first topic to discuss here, which is what the actual use cases were and where they got their parallelism. First, we see the 51 use cases, with 26 features for every use. Remember, we discussed those 26 features. This use case is, these are all defined here at this website. And also, there's a very complete discussion of them in my earlier course. We will not repeat this complete discussion because that went through every 51. Here we'll just go through a few of them to illustrate some key features. Notice where they come from. I mentioned government operations. There are 4 of those: the National Archives and Records Administration and the Census Bureau. Commercial, we had finance, cloud backup, Mendeley, a well-known citation company, Netflix, web search, a couple of use cases around digital materials, and one on cargo shipping. Here we have defense, where we had 3 related use cases. The actual sensors involved, what's involved with surveillance and imagery, and then deriving results, what's often called situation assessment. You have all your sensors, the commander needs to decide what all that means, and he or she has to be helped by the big data analytics. We had a good, healthy set of healthcare and life sciences use cases, medical records, various analysis methods around probabilistic methods around databases and graphs, area of pathology where imaging is very important. Bioimaging is also imagery, but of a different type where you have light sources bombarding materials. Genomics is well known to be important. We actually gave that as one of our examples earlier on in the data access section. Epidemiology, study of population level features, and then the use of people activity models, and then the biodiversity, which was one of the ones we actually did for the, we both did both of these, and actually these 3 in the sample we gave the 5 properties of deep learning. Well, deep learning is used to decide how to drive cars. We have the application of trying to geolocate images in cameras, Twitter analysis, crowdsourcing, the area of network science study, and the NIST benchmark datasets. In the ecosystem for research, which are rather general areas, have metadata, collaboration, language translation, and light source experiments. Astronomy and physics, we have a whole bunch of actually 2 broad classes. The actual astronomy class of gathering data from telescopes. We had a couple of accelerators, the Bell Accelerator in Japan, and the Large Hadron Collider, which is the one that is used to study the Higgs boson and the biggest in the world at CERN. In the whole broad area of studying the Earth, we have different parts of the Earth: polar, broad-based Earth science, including climate, environmental science, and then we have here these various parts of it: radar scattering, earthquake, ocean, Earth observation, ice sheet radar scattering, Earth radar mapping, climate simulation, atmospheric turbulence identification, biogeochemistry, and that's sort of environmental science. And here are a whole bunch of sensors that are being analyzed. Energy, as I mentioned, we're short of. We had an important, very interesting use case, the smart grid, but there are other important areas such as seismic analysis, where the companies go out and gather data with seismic data to decide where the oil and gas is located. Now, we're going to do parallel computing. The key aspect of parallel computing is to take something and decompose it into parts and place each part in a computer, because that's how you do parallel computing. You do domain decomposition, where we have a domain of what domain varies, and this is what this is discussing. What is chopped up? Well, a whole set of them that chop up people. When you do search, those users of search are actually analyzed independently, and you can put one set of users in one being serviced by one computer and another set by another computer. We can do that parallelism over the subject of the problem, or it's like when you're analyzing people's tweets, or by the people using the application. Then on a huge number, essentially they're studying things like images, electronic medical records, gene sequences, material properties, specification of manufactured objects, and also modeled entities like vehicles and people in grand-scale simulations. These items are actually parallelized in several different applications. The Internet of Things is this marvel of application where some 20 to 50 billion objects by 2020. There you have a whole bunch of sensors, and you're doing parallelism over the sensor because each sensor can send this data to the cloud independently. Another important source of parallelism is that over events. What are events? These are particular important characteristics or happenings which can be discovered, say, either in telescopes where you discover a supernova happening, or in credit card where you discover fraud, or in the atmosphere where you discover an event called a turbulence, which other planes need to be warned away for. Well, we have nodes in a graph, such as the semantic graph coming from the RDF syntax. We have actually learning networks, which have nodes, which tend to be a much more structured, simpler set of nodes. The deep learning is not simple, but the nodes in it are not the same structure as the nodes to say to relate drugs, doctors, and patients. We have parallelism over tweets, blogs, documents, web pages, etc. Very important parallelism. And you also have parallelism over the words and the characters inside those pages. Of course, we can have parallelism over files. We can read different files in different computers. And then when we do our famous high-performance computing, we can do parallelism over particles, cells, mesh points. We will not be discussing that because this is only indirectly big data, although we will mention the important concept that a simulation of, say, a turbulent flow or over, say, an aircraft or a combustion event, those simulations produce big data in the visualizations or the recording of what those simulations produce. All right, now if we look at these 51 use cases, we'll come and illustrate this parallelism later on because we'll look at particular use cases and we'll tell you how to parallelize them. So we derived a whole set of features. And here's the first set of features. And we will describe these features in more detail in the following slides. There's a feature called pleasingly parallel, which means that every item in the parallelism can be analyzed independently. We have the MapReduce feature, that the items can be analyzed by MapReduce. And we divided MapReduce into two types, the broadest type of MapReduce and a simpler type of MapReduce, where effectively the so-called reduction operation, which gathers the data after the independent maps have done their thing, is simple statistics, adding things together. That's seen in the Large Hadron Collider, where you add together the results of analysis of each event. There's an important type of MapReduce called iterative MapReduce, which is you see when you have sophisticated data analytics requiring in-memory caching to get good performance. The Apache system Spark and the Indiana University system Twister and HARP are of that type. Graph processing is important, and we found 9 of them. So this, by the way, is the number out of 51. So we have 9 graph, 23 iterative MapReduce, 7 statistics MapReduce, 18 ordinary MapReduce, 26 pleasingly parallel. So we have 9 graph problems, so that's non-trivial, where the entities in the problem, like the linked together in a graph, like the nodes of the deep learning network or the nodes of the RDF graph. Fusion is a well-known concept, actually a very old concept, and that point says that when you have a data problem, you actually often have variety, one of the V's. So that's diverse data, and you have to integrate these diverse data. Like you have to integrate the data on patient reactions with the information about pharmaceutical companies and hospitals to actually get the right answer. Um, the last property on this page is streaming, and it's a very important concept. Namely, you need to data is streamed, and you need to process it incrementally um, as it comes in. If you look at, for instance, sensors are producing streaming is like time series, or sometimes called time series. The data comes in one at a time, and you have to process it as it comes in. So the streaming is characteristic. Okay, so the next set of slides go into these features in a little more detail. So the first feature we have was pleasingly parallel. This is a very famous feature. It used to be called embarrassingly parallel because when we started parallel computing, we were sort of ashamed of that system because we thought we had to do difficult algorithms and problems that the algorithm was actually saying. Process each item in the domain independently. We didn't have to invent an algorithm. We did have to actually invent a lot of complicated software, but we didn't have to have an algorithm. And so this term, pleasingly parallel, was invented. Actually, I said it was originally we invented embarrassingly parallel, and then we changed it to pleasingly parallel when we realized that this class was extremely important. And in fact, when people did grid computing, this was the problem class they largely focused on. So as we say here, in parallel computing, you focus on organizing the computers to solve a problem. In the pleasingly parallel case, that organization is pretty straightforward. You do have to do load balancing, but you don't have to do a lot of synchronization. So a good example of this is in search. When one user accesses a search site, the other user can be done totally independently. So each user can be analyzed independently. So that's a pleasingly parallel example. In the Large Hadron Collider physics case, we have lots of, many billions of events, each of which happens to be around 1.5 megabytes in size. And those events can be analyzed independently. So they're pleasingly parallel, and actually 300,000 cores around the world kept busy doing this independent analysis. So there are some correlated events, but they're largely uncorrelated. And we have reductions, and actually Large Hadron Collider has such reductions, but they're a very minor part of the problem, and usually don't think of it in this fashion. So when you have pleasingly parallel applications followed by gathering all the data in the very simple statistics, reduction, counting the number of times things happen over all processors, that I call MR stat. So in general, of course, we can generalize the search case to users accessing a database or sensors accessing clouds. Those are examples of pleasingly parallel problems. We will return to this graph and discuss it in different ways at different times. It's a very important graph because it tries to actually point out that if we look at the problem structure, we can think of it in terms of MapReduce of 4 different types. Here is number 2 is the brilliant invention of Jeffrey Dean, classic MapReduce. Maps followed by reductions. Pleasingly parallel, there is no reduction, just maps only. In fact, MR stat is an example where these reductions are particularly simple. Iterative MapReduce I mentioned, actually similar to classic MapReduce, but the whole job involves multiple MapReduce, or what we call map collective, map followed by communications. And those results have to be kept in memory to get good performance. The final form of map reduce is actually that well known in high performance computing, where you have a lot of point-to-point communication between the maps. We call it map communication. It's illustrated here for a graph, which is seen a lot in big data. In the case of simulations, you get a lot of these sort of local type of communications, because you have differential equations, which you don't get in big data, but in simulations you have differential equations, and those, when you discretize them, give you local point-to-point communications. So here we have the types of software, MapReduce and iterative extensions for these three, MPI and Giraffe for this fourth type. We can try to integrate everything together, such as in the Dupe plus Hart model, and we have examples here of the different types of work. Hello, we've already discussed the graph category and its general characteristics. We have a class of problems where the data items are linked together. Actually, the data is both the items or the nodes of the graph and their linkage. And that for a graph problem, typically the studying such complex linkages is pretty hard. And there are various important algorithms. If you go to Wikipedia, you'll find 92, which tend to be rather difficult to parallelize and sometimes are hard to do on distributed memory and things like that. Studying of graph algorithms is an important area of research. The software Giraffe and Pragal are typical of those that support graph. And this corresponds sort of also to the fourth form of MapReduce in our previous discussion, maps followed by point-to-point communication. Let's illustrate that. Here we have an RDF graph. Let's suppose we store those three nodes in one computer and these three nodes in a different computer. Then when we're doing a study of this graph in parallel, this computer will look at these nodes, the other computer will look at, or other process will look at these three nodes, but they are linked together. And these linkages cross the processor boundaries. And that will turn out, when you implement the algorithm, into a communication between these two processes, because this particular node here will need to know the properties of that node to study, to update the state of this node, and so on. So communication is related to links that cross processor boundaries. And graphs are hard because those links are often very irregular, and dealing with irregular point-to-point communication is tough. Here we see some other graphs. Here we have a cortex, which obviously has a very complex neural structure. Here we have a word chart. And this, if we convert it into a graph of these entities and their linkage, would obviously correspond to a pretty complicated graph. The next slide has a more sophisticated example showing that biology can produce really complicated graphs of, and trying to understand this is certainly a difficult technical problem, which I say underlies all this research in graph-based processing. This is not an area I'm terribly knowledgeable in, although I understand a lot of the broad issues, especially the parallel computing issues. So this is the final category we're going to discuss here, fusion and workflow. And I told you why data fusions are important. You have different types of data which need to be integrated together to get an answer. It's often related to the concept of knowledge management, and it involves some high-level integrating of different parts of the data. It tends not to go into the level of the individual data items, but it goes to classes of data and conclusions from that classes of data, and bringing that together to get a final answer. And I say this is something to do with the variety feature of the big data Vs. And if you look at We will come to a slide later on where we have raw data, the data to information, to knowledge, to wisdom, to decisions. This is the pipeline which we use in all of data analysis. These different steps are more or less important. And this shows you this variety of data, this particular graph. And workflows are often how you integrate this fusion, because workflow, I said, is how you take different jobs and put them together to make a big answer. So fusion is taking different types of data and putting them together to get an answer that is implemented as a workflow. So the fusion can be done really simply by just running the different varieties of data independently and placing the answers on a portal, and then the user does the integration. Or else you can have a sophisticated artificial intelligence algorithm to make the decision. So either the decision maker does it or the computer does it. All right, so that discussion is done in more detail here. So here I added 5 types of MapReduce because I separated MR stat and MR. I called them number 2 here because they correspond to number 2 in the previous graph. So there are 4 pictures, 5 types, and these are how we classify. We classify things as graph, MR iter when there's iteration involved, MR stat when there's a really simple final reduction, MapReduce for the general case of MapReduce, and pleasingly parallel, which is the map only. And actually, this is illustrated on the previous slide. I changed the order. And the parallelism comes from dividing something up that's very big, such as the set of all events in the Large Hadron Collider, and taking lots of processes or cores, and each process taking part of the problem. That's how the maps get done. All of these problems have maps, which are taking some data, where the data is decomposed, and you take the data in your current core or current process, and you change it. And that changed result is then typically written to disk. That's the classic map reduce model, or it's communicated to other processes. That's the typical iterative MapReduce case. So if there's no communication between the processes, that's map only or pleasingly parallel. Classic MapReduce has 1 map per process followed by a reduction. MR stat is a special case of the above with really simple reductions. MR iterations is map, reduce, or more general communication, typically a collective communication. By collective, we mean that all processes are doing things, sending information to all other processes or some important subset of them. And that happens, and then we have to go back to the beginning. And as we have to go back to the beginning, we must keep everything in memory to avoid writing to disk and reading from disk, because that dominates then the computing. And we described how graph could be important. So now we get on to the analysis of the streaming category, which was the final category of that initial set of features. We will do that in part C of this unit. And so we'll sign off here and rejoin you again in part C. Thank you.